start with our first keynote, which is Nicolas Wu. Most of us know Nicolas. He's a very active member of Haskell Symposium and the Haskell community. So he's at Imperial College, where he leads the functional research group. And before he was at Bristol and Oxford, where he did his PhD. And he works on category theory, semantics, and effects, obviously. And today he's going to talk about the evolution of effects.
Okay, well, hi everybody. It's a great pleasure to be here at Haskell Symposium. And indeed today I'm going to be talking about the evolution of effects. So this talk is not going to be your ordinary sort of Haskell-ish talk because there's going to be very little technical material here. This is actually going to be a history lesson for you. So let's see what it's going to be about. So I'm going to start with basically a history of the evolution of effects. So where did they come from? And starting with the history of programming languages, we're going to move on to the history of monads, effect handlers, and then possibly onto higher order effects. So that's the itinerary. So the caveat is that when I'm trying to do history like this, there's no way that I'm going to be able to talk about all of the history to the degree that I want to. There's just far too much to cover, and so I apologize in advance to anybody that I omit, or anything that doesn't happen, or if I do things in the wrong order. Surely there will be mistakes, but I'm doing my best. So I think the story starts really with this big dichotomy between functional and imperative programming that starts right at the beginning of computer science, and right at the beginning, by which I mean between Church and Turing. So of course Church saying the way we should do computation is with lambdas, and Turing is saying we should be using assignment. And maybe there'll be an eternal separation between church and state, and since we are in the states, we have Jefferson on your $2 bill saying that the First Amendment was establishing that indeed there would be an eternal wall of separation between the two. And so since we're doing history, I thought I'd flash up on the left-hand side the Bill of Rights, where Article 3 is saying that there should be a separation between these two things, and then his explanation to the Banbury Baptist Association that indeed that's what they meant. So perhaps there's no hope of sort of making these two things come together, but we should try. So let's have a look at the history of programming languages. And it really is history because I'm going to take you back to 1666, and London is burning. And what's happening in 1666 isn't just that London is burning, but also that this chap here, Leibniz, has finished his PhD dissertation. And his dissertation is on the art of combinatorics. And it's about a proof of the existence of God from some fundamental principles, an alphabet of human thought, and the idea that all concepts are combinations of a core set of concepts. So he's thinking about modularity right from the beginning. So he writes a letter to one of his friends saying that one day he was on a ship on his way from London and the weather was bad and he had nobody to talk to apart from sailors, and so he decided to design a rational language. And so he's probably the first programming language designer as well, thinking about a way we could have a way of reasoning about metaphysics and morality. So that's a letter to one of his friends. And so yeah, maybe he was the first programming language designer way back then. Moving forward a bit, at a different keynote elsewhere, Dubois-Reymond says something like, ignoramus et ignoramibus, about the nature of knowledge and understanding. Basically, the stuff that we do not know and that we shall not know, that we should just not try. At the same conference, but a few years later, so this is 1930, Hilbert replies to that ending of a keynote with a different one, saying, "Wir müssen wissen, wir werden wissen," we must know, we shall know. And he tries to establish then, together with Ackermann, a whole bunch of open problems, and one of which is the decision problem, basically saying, given a question, is there a way of answering yes, no to that? And that opens up, of course, the answer, which is no. Gödel introduces the incompleteness theorem and says, actually, there's no system of logic that you could produce which isn't complete in its own right. And then that idea is taken further by Church and Turing, who also say, yeah, we really have a problem here. There's no algorithmic way. There's no system that we could use or design that will solve this problem. And they do it independently and from two completely different perspectives, which I'm sure you all know about. Moving on a little bit furthermore, we get the work of von Neumann. So von Neumann picks up on the ideas of Turing and starts producing the first computer, or at least designing the first computer. And that's a very, very contentious statement because so many different claims to first computers come about. So the Americans have EDVAC in 1949, although they are I think, scooped by the British, although silently and in secret the year before, but again, that's a highly contentious statement. And eventually, these computers need programming, and so fast forward a bit, you get the invention of Fortran by Backus. And this is a nice language because for the first time, you're not just putting instructions on a machine, you have equations and you're able to sort of do some formula translations. But actually, Backus says that although people think that formula translations was a big contribution, his reflections tell us that he thinks it was actually about the structuring and organization of loops. So very early on, we're already seeing that the problem with programming isn't so much equational stuff. It's trying to understand effects. It's trying to understand sequencing and control structure. That's the difficult part that he thinks was the good contribution of Fortran. Meanwhile, in the functional camp, Lisp is created in '58 by McCarthy. And I hope you can see right up here, there's a bit of lag, that he has the lambda calculus in play right from the beginning. So we have a whole bunch of lambdas in the way the thing is designed. And he has this notion of conditionals. He has recursion. This thing's not working. He has recursion right from the go for factorials. And he also has the map list function appearing way back in the late 50s. So he's doing real functional programming with lists where head and tail are called car and cudder, of course, because they correspond to the machine instructions that you want to be using for these different constructions. And he even coins the term abstract syntax in '62. So these ideas kind of come together, or at least these people come together in '58 in the invention of ALGOL. So together with Peter Noir and a whole bunch of other people, they tried to design a language which is good for expressing algorithms. And so this language, Tony Hoare tells us, is a language that's so ahead of its time that it was not only an improvement on its predecessors, but also on nearly all of its successors. Including Haskell. That language was interesting because it's a very imperative language. And it's not long before, in '65, we see Peter Landin starting to work on how we can combine functional and imperative thought into a single paradigm. So he has this notion of what he would call applicative expressions, which is just a fancy way of saying he wants there to be some syntax for lambda expressions that isn't literally just writing lambda x dot blah. So he has let statements and ands and recursive lets and this sort of thing, and he thinks that that's a good way to go forward for the programmer. And he adds to it an assignment operation to come up with what he calls imperative applicative expressions and a machine that interprets these things. Okay. In '65, so shortly after, he shows a correspondence between ALGOL and these imperative applicative expressions and shows that there's correspondence between these two languages. So I think this is a nice establishment of the theory behind why ALGOL was really a functional imperative language from the go. So in '66, he writes a really important paper about the language ISWIM, which stands for If You See What I Mean. And this is called the Next 700 Programming Languages, and lots of other papers have the Next 700 named after this paper. And what this paper is really, I think, is it's a predecessor to Haskell. It has things like pattern matching, it has where clauses, it has garbage collection, and it has indentation sensitivity. So all sorts of things come out of this paper. I mean, some of these ideas are in other places, but this is where they all come together. So he writes things like this, which you could practically type into Haskell, and things would work. And it's an interesting piece of history because at the end of this paper, the questions that were asked during the conference have been transcribed, so you can see what the conversation looked like, and it's fascinating. Peter Noir says, regarding indentation, in many ways I'm in sympathy with this, but you would regret it because of the kind of rearrangement of manuscripts done in printing. And if you've ever written a paper in Haskell, you know kind of what it means. But actually, I think it's a positive thing that the indentation is there because you can play around with it a lot more when you're trying to typeset things, but it is painful. The other thing that's interesting about this paper is that he equips the language with a whole bunch of equivalences for reasoning. So reasoning features very highly for him. He wants sub-expressions to be such that if two sub-expressions are equal somehow, then that means something about the greater expression, so there's a notion of congruence. He wants there to be equivalences between definitional things, so lets and wheres should somehow be equivalent. Built-in expressions like this is an if-then-else statement, there should be a way of understanding that equationally. And probably the thing that's most interesting to me is he wants there to be user-definable DSLs from the beginning. He wants users to be able to define their own small languages with equations, and iSwim should be able to interpret those languages for the needs for the means that they're for. So DSLs are featuring very early on in this work, although again, that's not what they're called. So he says that these primitives should allow people to write equations between them. And I'm thinking about algebraic effects, which is all about operations and equations. And this is kind of being pointed to at a very early stage here. And around this time, structured programming starts to become very fashionable. So Burstel in '62 starts saying that we should be able to do proofs by induction over the structure of the input. It's an old idea even at this stage, but he makes it quite clearly here with these very early implementations of what looks like fold right and concat right from the get-go. And he's writing in iSwim, and he shows that you could write a program for doing sorting via an intermediate tree. And this is the kind of thing that is very close to the Haskell you'd write in a sort of first-year course, I guess, and a proof of its correctness by induction. So these are some nice ideas coming together, and it becomes very fashionable in the '70s with a big book called Structured Programming, which is kind of famous at the time, where there are certain close analogies between the methods for using structured data and the methods for structuring the program which processes that data. And that sounds very familiar to those of us who like folding and catamorphisms and all that sort of thing. These ideas are being pointed to in the '70s. Back to the 700 programming languages paper, we have Landon saying that another really important thing that he wants to stress is this idea of denotational semantics. So he wants it to be such that the meaning of the whole is in terms of the meaning of the parts. And this is a critical point for him in the semantics that you give to the user-defined expressions. So how are we going to give a meaning to these things? Well, through a kind of structural induction. So essentially, he's harkening forward to denotational semantics, which comes up a few years later. So denotational semantics, the paper there is in '71, which is something like 5 years later. And that's by Darren Scott and Chris Strachey, where they have this equation right here in the middle that says exactly what I just said a minute ago, which is that the meaning of an expression is given by the meaning of its parts in composition. So this is a really critical idea that's coming out, again, all from the '60s. But actually, as I said, history is complicated, and this is definitely not completely true. It even came up before that, but that's a good place where to start. So what I'm trying to get across at this stage is that the idea of the separation between computation as lambdas and computation as assignment is kind of murky from the beginning. Yes, there's a clear separation between the two, but there's a synergy between the two that's going on as well. People are thinking about how these things can be combined from the beginning. And so perhaps the question isn't so much how can we keep these things separate, but maybe there's a way of combining them together. And Landon has something to say about this in that same paper again. He says, iSwim brings into sharp relief some of the distinctions that other authors are intended, such as adjectives such as procedural, non-procedural, algorithmic, heuristic, imperative, declarative, functional, descriptive. Here's a suggested classification and a new word. So the new word that he thinks that classifies all of these different paradigms is denotative. He thinks that denotative semantics should be the way that we think about programming languages, whether they be imperative or functional. That's the kind of the system that we want. So it's not so much about having a separation, but maybe some kind of synergy between side effects and field functions, and understanding that synergy in detail. So what would denotative look like in the context of effects? Well, it means that we need to have a way of being able to reason about effects and how they're carried around and how they influence one another. And I think that the monads is a good way of doing that. So why on earth do we have a picture of a burrito? Well, there's somebody in the audience to blame for that, which is Brent Yorgi wrote in his blog in '09 something about a fictitious person called Joe who's trying to learn monads and thinks that burritos is the right way to explain them. So even though it wasn't Brent himself who came up with monads, it was his fictitious Joe in his head, he's still to blame for this. He thinks that monads are like burritos. So I'm about to do a prehistory of monads, but monads in the context of this community. So in order to do that, I really need to go far back into ancient history of the memories of Haskell. And so I'm going to bring you to South Africa in 71,000 BC. What happened in 71,000 BC? Well, we have this rock. And this rock is actually the first object that we have that's been written on by any man at all. And so scientists have done some research on this rock. It comes from 73,000 years ago, and it was found in a cave somewhere in South Africa. And scientists have done some very careful analysis on this rock. It turns out that they've looked at the inscriptions very carefully, and they said there's no way this is coming up in nature. This was drawn with some crayons, and if you look very carefully at the inscription that's there, you can see that mankind has been striving for Haskell for a very long time. Actually, this is the real ancient history. I'm not sure if South Africa 71,000 BC is when this picture was taken, but here we have lots of different people from even in this room coming together, and there's a beautiful paper about history of Haskell being lazy with class, which goes through some of the history of Haskell in much more detail than I can now. And I just want to pick out that, according to that paper, obviously monads are one of the big inventions that came about, or one of the good things that came together for Haskell that worked well. So let's talk about where monads have come from to get a sense of that. So as I said, this talk is nothing to do with technical detail. It's a completely historical note. So let's think about monads and where they're from. So the kind of classic reference for all things category theory is this famous book, Categories for the Working Mathematician by Mac Lane. And he writes about monads in that chapter, and he has this little note that basically says, well, we didn't really realize how simple and important monads were for quite a long time. And he has two references for this. He says that he made a little note somewhere in some paper, and then they were expanded upon. So let's find out where he thinks monads were first referenced. So I did some digging around, and you come up with this paper. It's in French, and don't worry if you can't read it. Most of the slides you can't read what's on there anyway. The point I'm trying to make is it's in French, and it's difficult to read. And this tiny little four-liner is what he's referring to when he says that he invented monads or talked about monads from there. And if you read this carefully with the eye of category theory today, you might be able to see that he was talking about monads to a degree. But I think it's difficult to sort of establish that this is the beginning of monads. The beginning of monads comes much more clearly through the work of Godement, which again is in a French treatise on topology and sheaf theory. And if you look at that paper more carefully, you will spend hours, perhaps days, going through a whole bunch of French mathematics and find that after 260 pages, monads are not mentioned anywhere, except when you get to the appendix, and you think that's why this is the reference to this, because in the appendix, Roger Godement has these statements where clearly this is monads, right? So basically he has a definition of K being return and P being join hidden away, and he brings in what we now call the Godement calculus, which is the theory of what we call whiskering, which is a way of talking about natural transformations and functors in a very categorical language. But the equations A and B that we have here are exactly the monad laws that we would write today in category theory. So the first one is basically the identity laws that says something like return, which is K, is the identity of this monoid, and then the associativity is the second part, or at least the join laws come out from the second part with P.
It's 1958 again.
And it's 1950. Yes, exactly. Yes, indeed. Yeah.
When I was born.
Ah, okay. It's a good year. It's a good year. It's an important, very important year. I should have added that there as well. Sorry. So for years, monads were simply called the standard construction, or the fundamental construction, or simply just triples. So people have had troubles naming things for a very long time as well. And it wasn't until quite some time later that the term monad actually appears in this context. And that's by this chap, Jean Benabou, in 1967, and he's starting to write about bicategories, of course. And this is a generalization of the idea of monoids, and he says that because we're playing with monoids, these things should be generalized to this concept of monads, and it's coming from that particular example, but also that later on, he's going to talk about polyads. And don't ask me about what polyad is, because I don't know what a polyad is. And so that's where the term monads comes from. Okay, so let's think about where we've arrived. So we've got monads, but I haven't really told you about category theory in computer science, and so I spent a few weeks digging around there as well, just to get a sense of where it came from. So we've got the introduction of category theory, and I didn't go into the beginnings of that in this talk, but I was tempted to. So the categorical semantics of computer science really come in quite clearly in the work at IBM. It's possible that there were things before this as well. It's actually quite difficult to separate computer science from mathematics when you start thinking about things like automata, and automata theory. And that's where a lot of these things started out. But some very early work is by these people. So Eilenberg and Wright start talking about automata theory or generalized automata theory and algebra. And they're thinking about universal algebra. So universal algebra is the study of essentially operations with equations. Sounding familiar? And operations with equations are, at the time they know, are Lauver theories, and they just want to study how these things work together. And some of these things say something like, the basic language for these are categories, and we're working with Lauver theories for the obvious reasons. So this is already in the sort of DNA of computer science from some very, very early on, so it's like 67. What I find interesting is this little clip from the paper which says, it's clear from this introduction that this paper contains nothing that is essentially new, except perhaps for a point of view. So, when I write papers that have some category theory in it and the reviewers say, there's nothing new in this paper, the point is the point of view that's the new contribution to these things, and that has been all along for a lot of these important papers. So sometimes just seeing a piece of research from a new perspective sheds enough light on something to make it clearer, and I think that's a very valuable contribution. So that's what they were saying right from the beginning. And actually, a lot of these ideas get crystallized and worked on by this chap called Elgert. And so he's thinking again about automata and how that relates to category theory. He, from his first paper, is thinking about Lauver theories. And then in 73, he talks about monadic computation and iterative algebraic theories. He's thinking about algebraic theories from the beginning. And I think what's fascinating is that it feels to me as a researcher in functional programming, when I started doing research in functional programming, that all the category theory had kind of like been evolving towards monads for a long time, or that somehow it was a novel invention. It turns out it's not been a novel invention. It's practically the first application of category theory in computer science was monads. But I think it's so hidden away in history that we've kind of forgotten these facts, and I think that's fascinating. So what he does in this paper is he connects Lauver theories and monads to study Turing machines. So amazing connections going on right from the beginning. Okay, where else do we go with this? So MacLean has his hand in this too. So he knows about the work of Elgert and people working in IBM on category theory. And at the time, he influences the young Goguen and says, you should go there and work on some problems because IBM are interested in categorical semantics. So Joe Goguen was apparently in a lecture series of MacLean's at the time when he sort of was told that this would be a good research direction for him to go into. So when he gets to IBM, he teams up with Thatcher, Wagner, and Wright. Elgert was there as well, but I can't find any papers written by all of them together. And they form this group that they call the ADJ group. ADJ because they're the first letters of adjunction, which is an important categorical concept. And they write this paper called a junction between computer science and category theory as a big pun. And their idea really is to write a series of papers which will be a complete retelling of the way we do computer science, very much a la Nicolas Bourbaki. So Bourbaki was a fictitious character that mathematicians had invented sometime before in the study of, I think, algebra, is that correct? Basically, it was a bunch of French mathematicians who got together and said they wanted to rewrite mathematics from a unified perspective. And they didn't want to write these papers with all the collection of all these people. So they invented this man called Nicolas Bourbaki, and he was the person that wrote all of these papers. And these guys are doing the same thing, but the group is called ADJ. And so they're very clear that the four of them, the author order is not in that order. It is a set that we should be considering here instead. And then for various reasons, it turns out that they were forced to write their names, and so this is how it worked out. Where do we go from here? They intended to write a whole series of posts towards category theory and how it relates to computer science, but they never made it past the first two parts of this. And this is like part one and part two of volume one of an entire thing that they had in mind, and then it just stopped. Classic. So in 77, they have a paper about initial algebra semantics from the perspective of category theory. So the idea here is that we have abstract syntax, and we want to give a semantics to abstract syntax, and of course the right way to do that is to think about what we call initial referential algebras, so this is free structures, and then what we have are being called homomorphisms from free structures are the way we should interpret these things. In other words, you provide me with an algebra, and I'll provide you with an interpretation of things. In other words, this is like starting with a list and folding over that list with a given f and k to give you the final result, except it's all generalized. So those ideas come in around 76 or so. And Burstall and Thatcher talk about this paper as well, which is where they start using monads to explain stateful programming. So in this paper in 75, they said they're going to be using some monoidal things or monadic things, and they have this little diagram where the semicolon is exactly sequential composition of sequential programs. So monads appearing in 75, at least in that setting. And that's not the history that most people will tell you when they ask where did monads come from in the functional programming community. They will normally tell you a slightly different story. And that story starts, I guess, with Dana Scott. Dana Scott was thinking about what would the theory of the lambda calculus look like. And that was in 1980. And what he surmised was that the theory of functions should be based on something, and it should be based on the theory of category theory. That's the right abstraction, he thinks, for thinking about functions in the first place. And so he says, what kind of theory should we be using? Everybody knows it's got to be category theory. And he wants a very sort of pure theory of this to be there. The idea is picked up by Eugenio Moggi. Eugenio is thinking about the lambda calculus and how he's going to give a semantics to that. And he takes the view and uses monads. The monad should give a semantics of lambdas. And so he gives this paper where he basically says category theory should give the semantics of computations based on monads. And he also wants to give an understanding of concepts such as state and exceptions and how they should be modeled. And so he very explicitly starts talking about those two functors in that paper. Again, side effects with the statement and exceptions are sort of really the contribution that Moggi has in the context of the lambda calculus. In 91, he extends that paper with a whole bunch of other examples for different notions of computation that we know and love today. So things like partiality, non-determinism, side effects, exceptions, and so on. So this is kind of a good treatise of the variety of things that are monadic, all in one paper. Okay, but that's not exactly how things arrived in functional programming. This is about lambda calculus. So what about monads for effects, and where does the history of that come into play? So the story for effects, as we would understand them today, really comes about from this gentleman, Philip Wadler, in 85. He's thinking about how it's possible to have something like exception handling built into a language without exception handling being primitive to that language. So he wants there to be some kind of mechanism that from which exceptions are derived. And for him, he realizes that actually that's possible with lists and laziness. So if you have a lazy language with lists, you can also have exceptions. And so this is why we have the paper about what is it? How to replace failure with a list of successes. So he goes in and explains these concepts, but the term monad isn't appearing at all here. It's really just, here's a different mechanism for doing exceptions. His paper is picked up by Spivey. In 1988, he writes this paper, although it's not published for another 2 years. So Spivey notices that there's a connection between what Wadler is saying and category theory. So he notices that actually what you want for exceptions isn't lists, it's some other thing which he calls the maybe monad, and he introduces the terms just and nothing to correspond to the categorical notions that we have. So we're seeing back in 88, these are where these terms come from. And he uses return, join, and Kleisler composition, the fish in Haskell, in order to describe how monads should work together. So of course he doesn't call them return, join, and fish, he calls them succeed, prop, and question mark. But he's basically explaining how monads are fundamental to these different constructions in this paper. That's sort of monads for effects, but what about sort of sequencing things together? Well, that has a very related but slightly different history, starting in around something like 86 with the work of Richard Byrd. Richard Bird is thinking about the theory of lists. So he likes programming with lists, and he likes people to reason about the programming with lists in a kind of calculational style. And because he's thinking about calculation, he also wants that to be a theory of, or a collection of laws that we should be using to manipulate those equations from the go. And so he introduces this paper in 86 and 87, where he comes up with a calculus for functions for program derivation. And in that calculus, he shows things like, so this funny f star is like the mapping function of some function f over a list, and he shows some various laws and properties about that, and he shows this property here which says something like function composition and mapping should somehow be coherent with each other, and he gives the definition of what we would call the map function in that paper. But of course, remember, the mapping function isn't new. That was invented in Lisp right at the beginning of functional programming. But nevertheless, this is a theory of how that's all sort of compatible and useful for program calculation. I think that's the contribution that we have in the late 80s. And again, Mike Spivey looks at this work and says, hang on a minute, this is all to do with category theory. And he notices that everything that Bird has been doing is about natural transformations and functors and adjunctions and monads, which he explicitly says. And so in his future work, he says, well, clearly we want to be doing stuff with monads and all of this. Now, in that paper, he actually implements a variation of the free monad. Now, to give you context, if you don't know what the free monad is, it's basically just a monad for syntax. And it's the monad that's underlying what we would do in the effects and handlers story. So the effects and handlers story is all about starting with some syntax and then interpreting that syntax in some way with some semantic functions. And we see that happening in 89 already in Spivey's paper, where he defines this new data type called exp of alpha, which has a constructor var, and apply var for variables in your syntax tree and apply for nodes of syntax in that tree. And he shows that there's a function which he calls subst for substitution, and that's basically saying if you have a term and if you have a function that tells you how to replace variables in that term with a new term, then you're able to just sort of apply that recursively. And that's what we would call now monadic bind. So the bind for the free monad corresponds exactly to the substitution function. So this, I think, is the first appearance of bind in the literature. But of course, it's not written greater equals. Actually, does anybody know where greater equals come from? Because I actually don't. And I've dug around a lot, and I've got no idea. Nobody knows. So I've asked him, and he doesn't know. I think it's Spivey in lecture notes that when he taught me functional programming, he uses a right triangle, but it's a filled-in right triangle, and so but that's the earliest thing I can think of, and it kind of just creeps into the literature at some point, and nobody cares about it. So anyway. Let's carry on. Monads in Haskell. So where do we get to with this? Phil Wadler was really instrumental to the way we use monads in Haskell today. What he did was, in 1990, he started thinking about how we could use Spivey's ideas to write programs. But he doesn't like the way that Spivey's producing programs by sort of slightly difficult to manage functions all applying to each other in slightly tricky ways. What he wants is some clean notation to do this. And he introduces monad comprehensions, which are a controversial feature. I think they made their way into the Haskell report and back out of the Haskell report, only to be put back into the Haskell report something like a decade after. So the idea really is that he wants a cleaner notation to do these things. And in 92, he basically says, well, actually, monads are very useful for programming, and he gives a plethora of examples. So he talks about the standard interpreter, i.e. the identity monad, where basically function composition is what sequencing does for you. He has one about error messages, which is the maybe monad, but with a payload of data. Error messages with positions, which we might now call the reader monad, combined with errors. The state monad. Output, so this is going to be something like the writer monad, and he has non-deterministic choice, which is the list monad, and then he has this very odd one, propagating state backwards, which is completely bizarre. And he has a little note that says, this example may seem contrived, but this monad arises in practice. John Hughes and I discovered it by analyzing a text processing algorithm that passes information both from the left to right and right to left. To make this change in an Imperial language is left to the exercise as an exercise for masochistic readers. So I have no idea how they came to this example, but that's what they did way back. I'm sure John can tell us all about it later. Then we need to kind of think a little bit more about where monad transformers get to. So I'm kind of assuming, this being the Haskell Symposium, that people are fairly familiar with some of these concepts, but in case you're not, the idea with monads is that we have a way of sequencing programs together. But it's not necessarily the case that monads compose. In fact, from a categorical perspective, we know they don't compose very well at all. So what we end up having to do is transform monads from one monad to another by sort of equipping it with additional operations as you go. And so this is the story of how you start getting modularity into programs in that manner. So the story again starts with Wadler and Blott in '89 this time, and these chaps are thinking about type classes. So they want a kind of ad hoc polymorphism, but slightly less ad hoc than ad hoc. And so that's where type classes come from. The idea is, how can we make it so that we have specialized code for a particular context? And so type classes are born. They start with the example of nums and addition and multiplication with negate, and sort of they leave it there, as in the introduction of classes is for things of kind star. Mark Jones in '93 notices that that's a bit too restrictive. So he's thinking about how you might be able to use type classes for something like the map function or the fmap, the functor instances. And he notices that you can just about manage it with type classes as they existed at the time, but it's a horrible hack and it doesn't really work very nicely and it's not good to work with. So he thinks that what we really want are type classes to be also extended to constructor classes where you're able to take things of kind star to star as well. And so he introduces the first functor instance in that paper, which is exactly as we know it today. And then the monad instance, which is exactly as it should be, with just a functor constraint, but also with the introduction of bind and join as being the two primitives for combining things, both interdefinable in this way. He also introduces in that paper the idea of the state monad. So the issue here is that monads generally are not interesting. They're not interesting because all they tell you is that things can be put into sequence. They become interesting when you equip them with additional operations, and in this case, let's say, the operations of state. So if you can equip a monad with not just the fact that it's sequencing, but it's sequencing and you can update the state, now we're talking, and now we have interesting effects. So the state monad class is something that he introduces here to capture the idea of stateful monads in a more general setting. And it's fun to see that happening so early on, because quite a lot of beginner programmers, when they start playing with monads, work with a specific hard-coded state monad, and they work with the operations of that alone without thinking about the more general abstraction. But that's exactly what Jones does right at the beginning. So in that paper, it's '93, he also introduces the monad transformer, which I find astonishing that in the very first paper that talks about monads, he's also introducing monad transformers. So this is the idea that state M can take an arbitrary monad M and augment it with the abilities to do state. And so he introduces he shows that it's an instance of monad, he shows that it's an instance of the state monad, and carries on with that. There is a little wrinkle in his theory at the time, which is that the operations of the underlying monad that you're trying to augment with state operations, the operations of that underlying monad don't necessarily sort of get used in the current monad that you're working in. It's difficult to express those underlying operations in the current context. And so a couple of years later in '95, we get the monad trans idea coming in. So the nuance here is that there's a new function called lift, which allows you to lift or reuse operations from somewhere further down in the stack into your current context. And that's the contribution of Liang, Hudak, and Jones. So this is really the basis of the MTL library that we sort of have today. And I think it's good to sort of just pause and take stock of where we've arrived. So MTL, I think, sort of ruled the Haskell effect scene for about a decade from this point, relatively untouched. So the slight wrinkle was, should we be using functional dependencies or should we be using type families, sort of came a little bit later. But for a very long time, this was the standard that everybody used. And it was a good standard because you could have different effects layering upon each other and you could reuse things from further down the stack. So perhaps we could have just stopped there and we don't need any more research to happen. But of course, something did happen. What happened next was effect handlers came. And so what's the story with these things? Effect handlers are a separation between syntax and semantics, harking back to the 1970s. So the idea is that syntax is represented by the free monad for a functor that provides a signature. So the idea is that you tell it what kinds of operations you want to have, and you say it's possible to build a tree, a syntax tree with those operations. And from the semantics perspective, we have a fold over that tree that tells you how to interpret the tree in a very structured way, harking back to the 70s, where you've got this denotational semantics game going on again. So why do people start getting excited about algebraic effect handlers? Well, there are all sorts of reasons. So we have a syntax program. So imagine this is the program that you have. It's got some OR nodes. It's expressing non-determinism. It's a syntax tree. The point is that programs are syntax. They can be inspected. You can look at them. You can program with them. But rather than just doing willy-nilly functions over this data type, you want there to be a structured recursion over this, just like folds. And so you can give them a denotational semantics by having a handler that knows how to deal with the different nodes in play. Furthermore, these nodes are all what we call algebraic. Now, when somebody says, oh, it's an algebraic effect, it sounds like a very mysterious thing, but all it means is that essentially bind distributes into all of the different parts of the program. So if we look here, we've got some program OR PQ, and if you extract x from OR PQ and you continue with x, that should be the same as, if this thing is going to come alive, that should be the same as this thing here, which is saying you can either bind x from P and then continue with it, or you can bind x from Q and continue with that. So the continuation structure sort of passes into the parameters of the operation, in this case the operation OR. So that's what it means to be algebraic. Now, the next thing that algebraic effect handlers give you is this idea of being extensible, in the sense that your syntax trees needn't be fixed in terms of the kinds of syntax that they can represent. So you could have non-determinism. You might want to also add failure to this, or state, or whatever other fancy things that you want. And so you can modify the tree to contain different syntactic constructs. They're also going to be modular, which is to say that you can decide to handle certain parts of the tree, leaving certain other parts of the tree unevaluated, and then later on, evaluate those other parts of the syntax tree that you haven't yet touched. And you can keep doing this in succession until the tree is all gone, and all you're left with is the semantic domain, i.e. the result that you were looking for. And what's useful about this is that we're starting to break into the modularity problem that monads were solving with the MTL, but without the restrictions required of proving that the monad trans stack that you're building is correct. So when you're doing MTL-style monad transformers, you have a proof obligation that says that the lift functions really behave like you think they behave for all the different combinations of effects in play. The idea with algebraic effects is that that should come for free by the construction of the effect system itself, and that's sort of ensured by the algebraicity of the operations. So there's no proof obligation to be done here. It all comes automatically. That's kind of the insight that makes this useful. They're also flexible in a way that monad transformers aren't in the MTL. By this I mean, so on this previous slide, I've got the interpretation of OR using append. So you see on the top part of this diagram here, there's a 3-second lag, which makes it hard to do this. So there's a plus here as being the interpretation of OR, but there might be other ways of interpreting OR as well. So perhaps what you want is this left angle plus right angle, which says that we're interpreting this into the maybe monad, which is going to be left biased so that justs prevail on the left and nothings annihilate things to the right. So giving multiple semantics to a piece of syntax is actually quite a useful feature. You don't get that MTL style because you're locked into the semantics by the type of the monad that you're dealing with, whereas in the algebraic effects world, you can provide a function that determines how to interpret things as you go. This is a little bit akin to having, imagine if you had lists, And the only thing that you could ever do with a list was sum it, because the resulting type had to be an integer, and all you do is take the monoid instance of integers, which is, let's say, addition, and that's the only semantics that you get. But we all know that programming with lists isn't just about summing things together. We could do many more things with lists than that. How do we achieve that generality? Well, with fold right, taking in different parameters f and k. So we dynamically change the semantics that we assign to lists, maybe doing products, maybe doing lengths of things, by changing the functions that we give in. Similarly with algebraic effect handlers, we could lock in our semantics to a particular meaning, that's the MTL style, but rather we would want to change the meaning of the program as we go, very much like we did with lists, and we can do that by providing different algebras. So that's the kind of the philosophy behind this. Okay, they're also equational. By which I mean that you can add extra equations to your theory. So here I'm writing an equation that says all PQ is the same as all QP. In other words, this is a commutative semantics. Now Haskell doesn't enforce that this is true, but behind the theory, this is something that you should be able to do. Another thing is that they're pervasive, by which I mean there are lots of different effects in play. So printing, getting, putting, throwing, forking, reading, and writing. It sounds like Daft Punk. Do with these kinds of things. And finally, they're efficient. So the theory tells us that there's a way of doing fusion over trees, and that plays well with all of this as well. So there are lots of reasons why people get excited about algebraic effect handlers. So to get back into the history of that, we talk about Bill Levere and Levere theories and where they came from. So he wrote his thesis in '65, which in another historical note, it turns out that his supervisor, Eilenberg, openly admits that he never actually read his thesis until years later and had no idea what was inside it. So it was left relatively untouched for a while. But many people took the ideas of Levere theories, as we saw earlier, realized that they were important. John Power, quite some time later, in '99, came up with the concept of enriched Levere theories. Now, there were many, many extensions of Levere theories. They were used extensively up until this point. But Power wanted to have a way of talking about Levere theories in the context of computer science. So prior to that, Levere theories were over the category set, and that's not quite powerful enough for the kinds of things that we do in CS. Levere enriched things to make that possible. He then worked with Plotkin to write a whole sort of semantics for what algebraic effects mean, and why they're good for computation, and lots of different effects are relevant there. And then they come up with this lovely paper in 2002 called Notions of Computations Determined Monads. And the idea here is that they don't think that monads are the way of understanding effects. They're just a way of interpreting effects. So you can think of, so I think a kind of a crude way of understanding effects is an effect is a monad. That's not true. These people are saying an effect is operations with equations, and they determine a monad, which happens to be the thing that you're talking about, but it's the operations and the equations that you started with. They are the building blocks of effects, which then determine monads that you could then play with. So that's the conceptual difference that they have. The reason that this is all interesting here is because effects can be combined together in interesting ways. This is the work by Hyland, Plotkin, and Power in 2002 that shows that these things are very modular. And eventually in 2009, we get the work of Plotkin and Pretnar showing the distinction between operations and handlers of those operations. And the sort of the insight here is that operations correspond to ways of constructing effects, ways of constructing trees, and handlers correspond to ways of deconstructing effects, in other words, folding over things. So at this point, we're in around 2010, and I'm trying to summarize some history of where algebraic effects went from that point. And I must admit that I failed. Because here's the effects library, bibliography, which Jeremy Gallup compiled, where people get to contribute the kinds of things that they've been working on in algebraic effects. And if you look at this website, you will find pages and pages and pages and pages and pages and pages of papers. And so I struggled to kind of put this together into a coherent story. But the point I want to make here is that there's lots and lots of research going on in algebraic effects. It's very, very exciting. And although I could touch on all these different topics, I think it's unclear at this stage which ones are the best ideas, the most important ideas. And I'd rather let more than 10 years go by before we settle down and say, these were the biggest contributions, but there are many. What I'm going to do now in this talk is be less historical and much more opinionated and more about my stuff. So higher order effects and scoped effects are really where I stepped into this field. And let's talk about where the ideas for that came up with. And here's a funny story. So I'll take you back to ICFP 2018. We're in St. Louis at the Haskell Symposium, actually. So ICFP's just finished. And this chap, Rob Ricks, is sitting in the corridor hacking away, and I start talking to him. And he says, well, algebraics are really nice, but we can't express lots of constructs like if statements and try-catcher syntax, and that's really troublesome. he's working at GitHub, and they want to do code analysis, and they want to be able to have algebraic effects for every piece of syntax that you can imagine in every single language, so they don't have to re-implement everything for every different language. So they want to have a kind of compositional way of putting things together. But it's not working. And the problem is that for some reason, if statements aren't behaving, try-catch statements aren't behaving. There's no sort of algebraic way of dealing with these things, and it's bothersome. And I start talking to him and say, it sounds like you're after something that I'd call scoped effects. So scoped effects are syntactic constructs where there's some piece of code inside your operation that you want to deal with before you think of it as being complete. So I showed him a whole bunch of papers that I'd been working on. So this story starts in 2014, a collaboration with Tom Shriver's, Bernard Discoutier, and Dermoen. And we were thinking about how to do Prolog in Haskell. So we wanted functional logic programming. Fancy that, yeah. And so we wrote this paper called Heuristics Entwined with Handlers Combined. And the idea with this paper was that, well, if you have a non-deterministic computation, so here's the little OR tree that we had earlier on, as a Prolog developer, you might want to have multiple ways of interpreting this. So you might want to say, I want depth first search. Oh no, I want breadth first search. Oh, perhaps I want depth bound search, or I want just to get one result. These are different semantics that we might give to this tree. So, given what we know, this is clearly an example of algebraic effects. We have a handler for this tree, or multiple handlers for this tree, depending on what you want to do with it. So we use this to model basically Prolog as a DSL within Haskell, it turns out that these different handlers, DFS, BFS, DBS, and once, they all have related behavior in the sense that, okay, sure, they do different things in terms of their traversal strategies, but they're combined in the sense that if you search for fail, you get fail. If you search for return X, you get return X. And if you search for search, you get back the search. So these are just some laws that correspond to how these different handlers might behave. So there's a kind of an equational theory that relates all these different search strategies. But the trouble is that these search strategies are not algebraic. So the theory of algebraic effect handlers doesn't apply to things like DFS, BFS, DBS, and once, even though it feels like there's an equational theory that binds these things together. So they're not algebraic. Is there a way that we can somehow extend the idea was the connection that we had there. A little bit later on, so in the same year, we write this paper about effect handlers in scope. And the point that is that, as I said earlier, bind has to distribute nicely in algebraic operations. So this is what happens with fail, or, get, and put. But scoped operations don't behave in this nice way. So if you have catch ph followed by k, that's not the same as catch p followed by k, h followed by k. So let's try and understand this. Catch ph is saying, I'm going to catch errors in p and handle any errors with h. Once I'm done, I'm going to carry on with k. Okay, so that's what the thing on the left-hand side says. On the right-hand side, it says, I'm going to catch the program p followed by k, and if something goes wrong, I'm going to do h followed by k. And there's a subtle bug here, which is if an error is raised in k, on the right-hand program, it might get raised and raised again. And so that's not what we want. So it's not a correct semantics. Catch is not algebraic. The once example is not algebraic either. So once is the idea that you have a non-deterministic computation and you want to pluck out the first result from this computation. So once p bind k should run p, and maybe you get lots of answers, but you just pick out the leftmost one, and then you continue with that answer in k. And k might then fork off that answer into different subparts. But on the right-hand side, we have once p bind k, which says, okay, so p bind k would be you do p, you generate lots of results, and then you pick out one, which is the first one perhaps, and then you want to once that. That's not necessarily the same thing, because on the left-hand side, p might have generated one result, then k would produce like 10 results, say, from that. So the resulting thing on the left-hand side is 10 different results, whereas on the right-hand side, p generates one thing, k turns that into 10 things, but then you once it, so you only have one thing again. So again, that's not equational, that's not algebraic, it doesn't work. So the insight here is that free monads are a little too restrictive. They don't allow you to have internal computations that do something different. And so we generalize the free monad, which is this thing, to something slightly different, which is the higher order free monad, which looks like this thing. Is that exactly the same? No, there's a single parenthesis difference between the two. So if you look really, really carefully, there's like, down here you have a bracket, bracket, and over here you have bracket, a bracket. And apparently that makes all the difference. So the idea is that we're moving from a setting where signatures are given by functors of kind star to star to where signatures have kind star to star, where you go higher order. It turns out that gives you just enough power to fix this problem and work with it. So I showed Rob this paper, and he implemented it. He said, "Wow, it works, but is it efficient?" And the answer is yes. It does all fuse very nicely. So I showed him another paper and showed how fusion is completely compatible with this technique. And they went away and programmed something that was 250 times faster than other libraries that they've worked with. And they were very happy. And they shipped it into GitHub Live. And in production, they had Haskell running, doing on every single pull request, every sort of push into GitHub, they were doing code analysis running this code, which was great. So people were very excited about this because it allowed people to do sort of code navigation features in GitHub's website. And we wrote something about that in 2022, just explaining some of the details around that, which you can have a look at. So that's the story of scoped effects. But of course, I'm skipping out a whole bunch of history. So this is the fused effects library that came out of that work, which was initially almost a transliteration of the work that was in the effect handlers and scope paper. Of course, there are lots of other different papers that were preceding this one that were, in some sense, more important, and that they also gave rise to lots and lots and lots and lots of different libraries. So there's an absolute forest of things. Oops, there's an absolute forest of, oh dear, of trees. There's a forest of libraries. This has all gone to pot. And it's very difficult for people to choose which one they actually want to be using. So this is the kind of mess that we're in now with regards to the effect system. And it's kind of healthy because it's really an indication that there's lots of work to be done and lots of engineering decisions to be made, but it's also not very healthy because beginners have no idea which one of these things to choose. So I would kind of encourage the community to perhaps slow down a little bit and think a little bit and maybe collaborate with each other a little bit to try and come up with a sensible way of doing algebraic effects. Okay. I have tried to condense a lot of research into the past sort of hour or so. In fact, I've tried to condense the last 71,000 years of history into the last hour or so. And that's been no easy task. So, but the thing I want to just terminate on, the question of what next. Will there be one ring to rule them all? Is there going to be a kind of final algebraic effects handler library? I don't really know. We want this thing to be modular. We want it to be expressive. We want it to be convenient, and we want it to be efficient. All sorts of different design decisions. And this is giving rise to the various libraries that we're seeing today. So from my very opinionated perspective, the most important one of all of these is actually expressivity. I want my effects handler system to do lots of different things. We can work on efficiency later on. We can work on these aspects of convenience and easy syntax. And I think we can get around those problems. But expressivity is the real hard one to crack. And I think we've just about cracked it. Because of the scope problem, which has now been solved, that's sort of unlocked handlers to work in a much larger domain than before by having this tiny little augmentation from the free monad to the higher order free monad. Actually, later work showed that we could have various variations of this monad in play, whether or not you wanted to tell the user if you're doing something that's algebraic or scoped or whatnot. Later on, we did some more work showing that latent effects, where you have some ambient effect stuff hanging around, is also important. I won't go into the details. But is there one ring to rule them all? And actually, very recently, Tom Shriver and Bith Vandenberg have written a paper that's just been accepted about a framework for higher order effects and handlers, where they go for free H as being the way of doing things. And this is actually implied by the original thing we had in the handlers and scope paper, but with a slightly different interface. Actually, just this week, Zhixin Yang presented a paper about modular models of monoids with operations, the MoMoMo paper, which from the theory perspective confirms that this is exactly the implementation that we want. So I think that we are just about turning the corner in terms of understanding what we want from algebraic effects, but we're going to need quite some more time in order to make this a convenient and efficient library. So I have some code that works that is very expressive, and I'd love to release that to you all soon so that you can all hack on it and make it efficient and better, et cetera, et cetera. But it's not quite ready yet, so hold on to your horses. And with that, it's the end of my talk. Thank you very much.
Yeah, so thank you, Nick. That was a very nice talk, and I'm here to ask questions.
Hi, Sven Keidel, TU Darmstadt. So I've never used effect handlers before, so which of these libraries should I use?
I tried to stay away from answering that question. I personally like the fused effects library. I think it's a very good place, but it really depends on what you want. Are you after, expressivity, or are you after efficiency? Like it's just difficult. I think I would point you to the fused effects as a starter point, but it's not necessarily the best for everything that you might want. And I say that with bias. So I'd say it's very hard for me to answer that question today. Yeah.
Thank you. You've pointed to libraries. Oh, by the way, that was amazing.
Thank you.
You are the new Phil Wadler of the history of computer science. You must have done an awful lot of homework.
Yes.
Scary. In French. You'd enjoy Stephen Wolfram's writings as well. He's written a whole book like on combinators as well. It reminds me a lot. My question is to do with, you described various libraries, right?
Yes.
But a language like Coca has effects as a sort of, built into the language syntax. So how far can we get with libraries, and do we need anything built in beyond, some primitives to make it more efficient, which Alexis has done more recently?
That's a great question. I think the work of Alexis is fantastic in terms of making things more efficient. There were other ways of solving that problem, but that's a good one. I think there are two things that I would like to have. One is sort of you can get around it, which is algebras are a little bit of a pain to express in Haskell at the moment. Now, we can do them with just functions in the style of lists with the function f and the k parameter that sort of deal with things recursively. If you look at effect libraries, they have slightly more convenient notation to say, hey, look out for one of these things and do this with that. And you can kind of simulate that in Haskell using view patterns and projections and all the rest of it. But it feels a little bit kludgy and a little bit painful, and I think there are problems around error messages and sort of making this a more inbuilt first-class part. And I think we can probably engineer our way through most of that, but having that built into the language might be a good thing. The second thing that I think is really missing is actually something like row types in Haskell would be fantastic. A lot of what's going on with these effects is that you want to be able to pick out different effects and say, I'm going to deal with this, and I'm going to deal with that, and then I'm going to add this effect, and I'm going to take this one away, which is exactly what row types is good for. And a lot of these libraries kind of simulate row types, and we simulated row types using the data types a la carte methodology. But there are other ways of doing that, and the more modern ways of doing that using things like heterogeneous lists and pulling out different parts. But these, I think, are all sort of very engineering hacks around the problem that Haskell doesn't have row types.
We don't have the thing.
We just don't have the
We just encode the thing.
So give us row types, and things like this would just be a lot less painful. I think that would be, so those are the two, I think, big hurdles towards making this more first class.
Great. Thank you. I think I didn't understand all of that answer, but I think a blog post expanding on that would really be quite helpful because you're well positioned to.
There's one last thing I want to answer that, which is actually unsaturated types, I think, would be a really good thing to have. So I know that the paper is...
unsaturated type families.
Unsaturated type families would be very useful for making the kind of extracting values out of computations without having to unwrap lots of different new type constructors. I think that would be useful too. But again, that's not been implemented yet. So
we have a paper.
Yep. Yep.
Norman Ramsey, Tufts University. I want to sort of ask a question very similar to the first question. As a humble compiler writer, I was initiated into the world of monads really by two papers, both of which you mentioned. Phil's paper on, I'm blanking on the title, the 1992 invited talk at Popple.
Yes.
With all the interpreters. And then the monad transformers and modular interpreters by Mike Kudek and Hughes.
Yep.
Can you recommend one or two papers, just at most two, for someone who's really brand new to this to get immigrated into the world of algebraic effects?
I saw Sam Lindley just shaking his head. I could give the opinionated. I think that the handlers in scope paper I wrote is not too awful. There's a paper that I wrote with Tom Shriver's Maria Skalioff and Maciej Pirog, which compares monad transformers and effect handlers in terms of expressivity and what you can do with them. So if you already know MTL and you want to think, how would I use algebraic effects in that style, that's a pretty good place to look as well. So it's a good kind of bridge between the two. And I think early on when people were doing algebraic effects, there was a lot of hype and a lot of misunderstanding about what they could do. People were saying algebraic effects are strictly better than monads. That's not true. And that paper is about showing actually monad transformers are every bit as good as these, and it's just the convenience of certain features that you're looking for. So that paper, I think, for someone like you who probably knows MTL very well, look at that paper. So that's monad transformers and algebraic and modular algebraic effects as a good starting point.
All right, thank you.
Yep.
very tall in this room. Thank you. Hey, so you did a lot of research, and so something I noticed when I first learned about algebraic effects through the Pretnar and Power papers is they talked about Lothier theory a lot, but they don't feature any Lothier theory.
Yep.
They feature presentations of algebraic theory
Yes.
with operations and equations, like you talked about,
Yep.
which is much older than Lothier himself.
Yes.
Right? Have you managed to figure out, like you mentioned Power's thought about Lothier theory somewhere along the way. Did you manage to trace the idea from Lothier theory to that? Like, was there a research path that made that happen?
So from Lothier theories to sort of Power's observation, Plotkin Power's...
Well, I mean, they speak about it. Probably there was an inspiration for that, and
So I think it does start with the work by Power on enriched theories. I think he really was thinking about how you can deal with operations in the Lothier theory style with theories proper, and I don't think any of that really got forgotten in the work of Plotkin and Power. I think they were always about equational theories, as was the work with Pretnar and Plotkin on algebraic effect handlers. I think it's more an implementation issue that we don't have a good a way of dealing with equations, although we've got a paper that's under review that deals with that using cubical agda for the equations and quotienting and all the rest of it, and that's kind of that. But I think it's more the implementation hasn't quite caught up with the theory, is probably how I would say that. Does that answer your question?
Not fully,
Okay.
but maybe it's something we should take with pen and paper outside if you want to go. But
Of course.
The general point is, a presentation, like Lothier theory are presentationless, right?
Yes.
And everything in the papers, it's not about equation or anything, they're presentations.
Yes.
And it's important because you want to list your primitive operation.
Yes.
So it's a very different point of view than Lothier theories.
Yep.
But somewhere there, they are the inspiration. And
Yeah, I think it's there in the early work of Power, but let's talk about it more later. Yeah.
Sure.
Yeah.
Any more questions? So I have one. So you said you are going to release a unified framework for effects?
So yes, I think that the answer of should we do scoped effects or latent effects or all these different variations, which are generalizations of algebraic effects, that's lacking a good implementation. And I've got on my laptop right here an implementation that I think works really very nicely. It's good from the expressivity perspective. It's not at all optimized or efficient or all the rest of it. And there are much cleverer hackers like Sandy Maguire or Alexis King who are going to, or Robrix who will be able to take that and make it much, much better. But from the expressivity perspective, I think it's the state of the art. Yeah.
Good. Okay. Thank you very much. That was very nice.